At peak demand, modern data systems merge millions of independent records in milliseconds, restructuring disparate data points into a single, synchronized grid. In a typical user interface, this information is organized into rows and columns, functioning like a massive digital spreadsheet. Beneath that interface, each table exists as a formal mathematical construct called a relation. Every operation, from a simple sort to a multi-server merge, is governed by the specific rules of abstract mappings. To understand how these systems maintain accuracy at scale, we need to build the architecture of a database from its foundation in discrete set theory. By defining the constraints of these mappings, we can isolate how functions behave and identify their distinct properties. This progression leads directly to the core engine of modern data science, the join. These mathematical rules are what allow us to construct, scale, and verify the integrity of massive datasets. This matrix represents the Cartesian product. Intersecting every element of set A with set B creates every possible coordinate pair. The order is fixed. Flipping axes reverses the mappings. A relation is simply a subset, highlighting only pairs that meet our criteria. We can apply this to an airline network. If we have a set containing every city an airline serves, a Cartesian product would represent every possible flight path between them. The airline's actual relation only contains the specific pairs connected by a direct flight. This introduces the property of irreflexivity. Since an airline doesn't operate flights that land at the same airport where they took off, the relation never contains a pair where the city is mapped to itself. These connections are also not automatically symmetric. A direct flight from city A to city B is often part of a triangular route, meaning the reverse path might require an indirect connection. In this context, any database table is a relation, a filtered set of pairs representing only the combinations that exist in reality. We can place a stricter constraint on a relation. We can require that every single input provided generates exactly one unique output. This specific type of relation is a function. It provides a reliable rule for converting a parameter into a predictable result. This architecture relies on two pools: the domain, which contains all allowed inputs, and the codomain, which contains all potential outputs. This parabola, where y equals x squared, demonstrates how sets interact. The x-axis is the domain, and the entire y-axis is the codomain. Because squaring is never negative, it never touches the bottom half. The reached portion is the range. By defining the range, a system can instantly identify and reject impossible outputs before it ever attempts a calculation. This leads to a critical question for data integrity. Does a function guarantee that different inputs will always produce different outputs? This property is called injectivity. In an injective mapping, no two inputs ever point to the same value in the range. On the left, this linear equation is injective. Every x hits a unique y. The right parabola fails. 2 and -2 map to 4. Does it utilize every codomain value? When range perfectly matches codomain, it is surjective. Knowing if a mapping is injective or surjective tells engineers whether a data transformation can be reversed without losing information. When a function is both injective and surjective, it is bijective. This creates a perfect one-to-one correspondence between two sets. Imagine two large sacks of marbles. To check if they contain the same amount, you could try to count them one by one, but counting is prone to error. A more rigorous method is pulling one marble from each sack simultaneously. If both empty at the exact same moment, they are proven equal. This pairing process is a physical example of a bijective function. This is how mathematicians compare infinite sets. If a bijection can be established between them, we can prove those sets share the exact same cardinality or size. Bijectivity provides a standard for structural equivalence, allowing us to match massive datasets where manual verification is impossible. We can now return to the structure of a digital table. In this context, a database is just a visual representation of these mathematical sets. This demographic table records students as tuples in a relation. However, the data reveals a problem. Two different students share the same name, Payal Ghosh. Using name as a unique identifier fails the test for injectivity because two distinct inputs map to the same textual output. Databases solve this by using a primary key, like a roll number. This creates an injective mapping, ensuring each student is linked to a unique identifier. This identifier is a mathematical safeguard, preventing the dataset from becoming ambiguous as it grows. Consider a second table, student grades. It tracks marks using only those roll numbers, keeping the personal names separate. To generate a report card, we must merge these two disparate tables into a single view. This merge, or join, begins by evaluating the Cartesian product of both tables, connecting every row from the first set to every row in the second. The system then applies a relational filter, discarding every pair except those where the roll numbers match exactly. Because the roll number is injective, the two students named Payal Ghosh are correctly routed to their respective grades without any overlap or error. Every time you query a database, you utilize an engine built on the formal rules of set theory, domains, and relational mappings.